theory. Okay. So which part of the classical theory can we extend, and in which way can we do that? So the concept of partial group was introduced by Andy Chermak in his 2013 article on fusion systems and localities that was published in Acta Mathematica. Roughly speaking, a partial group is a set endowed with a partially defined associative multiplication with unit and inversion, what you would expect, essentially, right? An alternative definition in the language of simplicial sets. So why is that? The motivation behind that is the theory of fusion systems. So for those who are perhaps familiar to this, fusion system is an object that mimics the p-local structure of a finite group, where p is a fixed prime number. And to fusion systems, some time ago, we attach a concept of linking systems as well. Linking system is a sort of category, and we were interested in attaching a linking system to a given saturated fusion system in a unique way. That was done by Andy Chermak in this paper. But in order to do that, he told me once, well, he's an algebraist, let's say, and he said, well, linking systems are categories, and these are not familiar objects to algebraists. So I turned this into partial groups and localities, which is more appeal to algebraists. And then he proved this wonderful theorem. Then I thought, well, that's a good idea. The concept of partial group, which is defined in algebraic terms as a set with some partial defined multiplication. But we would like to have a definition which is more appeal to topologists. So we come back to topology. And so we used this alternative definition using simplicial sets that I think it might be convenient, for instance, in order to define extensions. And that's the aim of this talk, essentially, right? So essentially, to a partial group, we attach a simplicial set, which is the classical bar construction, essentially, right? So simplices here are written like elements G1, G2, Gn, where GIs are elements in this underlying set, right? And the usual definition of phases and degeneracies. And the other way around, to a simplicial set, you can just attach the set of one simplices, and in some cases, for some simplicial sets, this set of one simplices will have the structure of a partial group. So let me put some more rigorous definition. So in this language of simplicial sets, a partial group will be a simplicial set. Well, say with these two conditions, I would say this is a partial monoid to start with. Partial monoid. And so a partial monoid is a simplicial set which just one vertex. That's the first axiom. And the second axiom is that the spine operator is injective for all n bigger than or equals to n. So by a spine operator, I mean the first numbered n simplices of a simplex. So in a picture, if you write three simplex like this, and you numerate the vertices 0, 1, 2, 3, so for the spine operator would be different. So this set of simplices, this one, and this one, these three simplices, these three edges, right, would be the spine of this. So an n simplex, it corresponds a set of n first edges, and that's the spine. So we want this to be injective. So maybe you recognize that in case this is bijection, what you have is a group actually, or a honest monoid. So so that's the idea. So for the notation, since from axiom 2, every simplex is determined by its spine. So we take the edges in the spine, and we call the simplex like this, using the bar notation, right? So that's a convention. And then we define also a product operator, which is somehow like the back edge, right? So if in the picture, if again we have 3 simplex like this, with vertex 0, 1, 0, 1, 2, and 3, then I can give names to these edges, say A, B, and C, and then the product, which is the back edge, is this one here, right? And this is going to be called the product of A, B, C, simply A, B, C, right? So this is a way to define a product. Okay. Now the third axiom is that we need an inversion, right? So an inversion is an anti-involution that usually we can write as with this usual notation: X is sent to X inverse, right? And this is the formal definition. We claim that that given a simplex denoted x1, x2 to xn, then the inverse is denoted x1 inverse, xn inverse, dots x2 inverse, x1 inverse, and then the product of all this, of both simplexes. I mean, this means, first, this simplex exists. Exists in our simplicial set, and the product is 1. 1, the unit, is defined as the degeneracy of the unique vertex that we have, right? So that's the definition of the unit, right? So that's that's a definition of the inversion, and that's these 3 axioms make this equivalent to the original definition by Andy Chermak, which is more in the spirit of group theory rather than simplicial set theory. Well, as you can imagine, a partial group is a honest group if the spine operator is bijective, right? A group. I was very happy with this definition because we have a whole theory of simplicial sets behind that. Until I saw that in fact these partial groups are not Kant complexes. So most of the theory we know about simplicial sets just does not work, unfortunately. Well, in any case, of course, so a partial group is a Kant complex if and only if it's really a group. Yeah, right. So, yeah. So, but in any case, we have concepts of partial group, homomorphisms. This is just maps of simplicial sets, so simplicial maps. To start with, we don't need a new definition. Homomorphism is just a simplicial map. Conjugation is defined in the usual way, but you have to be careful to have the necessary simplices in order that conjugation is defined. If you want to conjugate X and Y, then you need a simplex of this form to be in your simplicial set, and then you can define this as the product of these elements, which is X, Y, X inverse, right? So that's the way to define. But you need that this exists, if this exists. Otherwise, you cannot define the conjugation. Okay. So so the talk, this talk, I'd like to to briefly say something about self-homotopy equivalences of a partial group and extensions of partial groups. And if we have some time left, I'll talk about split extensions and sections of extensions, right?
May I briefly interrupt and ask a question?
Yeah, sure.
I just wanted to ask, when you say a partial group is an honest group, then you mean the set of one simplices is a group in the usual sense?
Yeah, right. Okay. So what I call a partial group as a simplicial set would be the bar construction on the group. Right. So the motivation, as I mentioned, is efficient. Skip the definitions of these notions. I'm sorry about that. A locality in particular is a sort of partial group that satisfies some extra actions. And this first work with Alex was intended in order to be used in a forthcoming paper on localities that we are preparing. Yeah, okay. So an example, say the generic example of a locality, a partial group, and in particular in this case, a locality, again, coming from finite groups, is the following. So you start with a finite group G and fix a silo P subgroup. P is a fixed prime number. And we choose a non-empty collection of subgroups of the silo, which are closed under taking over groups and G conjugation. G conjugation inside the silo. I mean, I'm not interested in groups which are not containing the silo, right? And then this simplicial set is defined as the simplices in the bar construction of G, for which I can find elements in this family in this collection of subgroups, such that I have a string of conjugation maps like this. So this would be, for instance, a conjugation map defined X is mapped to so Gn X Gn inverse, right? And if this happens, this simplex belongs to the locality or the partial group that I'm defining. Otherwise, it doesn't, right? So this becomes a partial group and indeed a locality that I'm not defining. With the right choice, the point is that, and this is our interest, with the right choice of delta of this family, you can prove that the P completion of this simplicial set we have already defined, you recover the P complete classifying space of the group. The point of this is that there are fusion systems having which are saturated fusion systems, which are not obtained from finite groups. And then this theory allows you to build classifying spaces for such exotic fusion systems. But well, I'm happy to tell you more about that if you have some questions. Anyway, there might be other examples, and there are other examples of partial groups for which this theory might be of some interest. So Antonio Diaz, Rémi Molinier, and Antonio Viruel have defined path partial groups, with which they are able to prove that every group can be obtained as the group of self-equivalences of a simplicial set, for instance, which is not at all obvious. Well, you can define a partial group with spaces of commuting elements. For a group G, you can define the partial space, the simplicial space, where the n simplices are the homes from Cn to G. And taking all together for every n, you build a simplicial set, and this will be indeed a partial group, right? Well, let's go to self-homotopy equivalences of partial group. So the first thing I want to tell you is why is all this is going to work, and this is the main observation for making all this to work. A very simple observation: a simplicial map from any simplicial set X to a partial group, or indeed a partial monoid, is determined by the restriction to the one skeleton, right? And this is just because this spine operator is injective. And that's, well, if you want to check, is immediate, right? And this means a lot, because also homotopies are easily determined. Once you have a homotopy, say between two homomorphisms, recall homomorphism is just a simplicial map, right? So you are given two partial groups or partial monoids, good enough. And two maps, F and G. And then the homotopy is something like that, right? So from G to A to F, and this is uniquely determined by one simplex, a single element, which is the image by the homotopy of this simplex in the product, which is 1, iota, where 1 is the unit, so the degeneracy of the vertex in H, and iota is the non-degenerate one simplex of delta 1, right? So in a picture, you could take this the vertex. Oops, sorry. You could take the vertex in H, and then so imagine this is a one simplex, so the degeneracy of this vertex, and then take iota. This is 1. Take iota. So, and you can draw a picture like that. So then you put F and compute the image. The image is going to be a given one simplex, which is here eta, that belongs to M, right? Of M. And then if you take any other one simplex X in H, and then you compute the images F of X, G of X. And then the point is that if this can be completed, there is a unique way to complete this, right? And observe that we have here eta again, the 4 vertices. Here is just one vertex because we only had one vertex. So we have, so we can form this simplex sigma 1, sigma 2. That would be the image of sigma 1, and here's the image of sigma 2. And then in this diagonal edge, we find this formula, right? This interesting formula, which is this one here, right? So this gives you the idea of the relation between homotopy and conjugation. This is not yet a conjugation, but almost. It remains to see whether we are able to really conjugate G of X. I mean, if we can multiply this on the right by eta inverse. I mean, if there exists something like that or not, right? If this exists, then this would be F of X. If it doesn't, well, we have this formula, which is so in some sense, conjugation is a stronger notion than homotopy, but it's almost the same in partial groups. So in groups, it would be the same. Okay, that's notation. So such homotopy is denoted by that. So we have homotopy between G and F, which is determined by this one simplex eta. Right. Recall that one simplex eta is what in the language of Chermak is an element of the partial group. All right. So here are some technical conditions that, if you are interested in, that ensures you that once you have this simplex eta and the maps F and G, the homotopy will exist. Right. If the homotopy exists, is uniquely determined by this element eta, but eta does not imply that the homotopy will exist. For this, we need some extra conditions, which are listed here, right? So if M and H are here is partial groups, exactly partial groups. So only just knowing F naught and eta, this will determine the whole homotopy. So F1 will be determined by F naught and eta, right? So for instance, that's very interesting because, for instance, if you take F naught to be the identity and you've got a homotopy of the identity, something like that, then the map that you obtain as F1 is determined, uniquely determined, just once the homotopy exists. And this is what we're going to call the conjugation by eta, which might not be really a conjugation yet, but but this is what we define by conjugation by eta, when this exists, right? And so here it comes the concept of normalizer of the partial group. If this was a group, the normalizer would be itself. But this is one big difference between groups and partial groups, which are not really groups, right? So this will be the set of elements, in M1. So I'm talking about one simplices right now, that define homotopy of the identity as defined before. So we have a homotopy between the identity and some other map. And this other map is conjugation by eta. So this means elements that define conjugation in the whole, which is extended to the whole partial group, right? Well, the center of M is defined to be the subsystem, the subset in this normalizer, defining a self-homotopy of the identity. I mean, the cases in which this is, again, the identity on M. In this case, we say that eta belongs to the center of this partial group, right? So the interesting point is that if M is a partial group, then this normalizer is indeed a subgroup of M. So this is a honest group, right? And the center is a central abelian subgroup in this normalizer, right? And then you can prove that there is an exact sequence of groups like this. So this is the map defined before. So an element in this normalizer is mapped to conjugation by this element as defined before, right? And then the center is by definition the kernel of this map, which happens to be a map of groups. That's a homomorphism. And the quotient is defined to be the outer automorphisms of the partial group, right? So in some sense, these are the inner automorphisms. In case of groups, this is the whole group, you know, right? But this is a well-defined group of outer automorphisms. Okay, so we get to the function complex of automorphisms of our partial group, which is what we need in order to say classify, for instance, fiber bundles, which is our objective right now. So given simplicial sets, just reminding the definition, right? So given simplicial sets, this function complex has n simplices. The simplicial maps like this from X times the n simplex, the standard n simplex to Y, right? So for a simplicial set, the automorphism complex of X is the subcomplex, which we will write like this, of invertible elements. That means invertible in every dimension. Maybe if you want to invert, you maybe want to extend this, write this like this way, right? Across. Or in the second component here, you just take the projection, right? And then it's clear what you mean by the inverse of this, right? So this is going to be a simplicial group, you know, very classical. Well, the point is that then we have this result that describes this topological group of automorphisms of our partial group, right? So it's classifying a space, fits in this fibration, where we have as fundamental group, we have the outer automorphisms of the partial group, and the second homotopy group is the center of M, right? And this is really the same what happens for finite groups, you know, or for topological groups. Well, so discrete groups, right? So we get exactly the same description. So with this in hand, we go straight to the definition of extensions of partial groups, right? And this was, for me, one of the motivations to define partial groups in this way, using simplicial sets, because because right, in this way, the definition of an extension is clear. It's just a fiber bundle, right? So an extension is just a fiber bundle like this with fiber M. So this is what we call extension of M by H. If you recall the theory of finite groups, so you know that there is a correspondence between, say extensions of groups, group extension, and fiber bundles of the corresponding classifying spaces, right? Fiber bundle, right? So in this case, our definition is this. So because trying to define a writing a straightforward definition of an extension, I think I didn't try actually, but my feeling is that this is going to be technical and complicated, because you know that not always you can multiply two elements, and you have to have this in mind all the time. And so a straightforward definition, I think it's complicated. However, topology provides us with a very clear definition of extension, which is useful in this case, right? So here's the usual definition of equivalence of extensions. So we can go quick through this. So how to classify? Now we want to classify extensions. How do we do that, right? So first we can. So we have extensions with in the base. So we have H in the base. So classifying this would be writing a map from this to the classifying space of out of M, right? So classifying, and these extensions are classifying such maps between this partial group and this group, say, right? And out of this, using obstruction theory, you get to the usual classification of extensions, right? By low-dimensional cohomology. But if you look at the theory of partial groups, of fiber bundles, you see that a fiber bundle is determined by a so-called twisting function. Twisting function that, well, I'm not going to go through the definition, but the idea is that in our case, this can be simplified to what we call a twisting pair, right? And a twisting pair, this is a concept that is borrowed from work with Ran Levy, Bob Oliver, and myself, right? So a twisting pair is defined like this. So let M and H be partial groups. So an H twisting pair for M is a pair of functions, T and eta. So T provides somehow an action, right? But I'm not claiming that this is going to be a homomorphism, right? It's just a map of sets, right? And we have some map from H2. So this is two simplices to the normalizer of M, right? So here it's written like that, right? So say G comma H, which is a two simplex, it corresponds an element eta of G H, right? Which is an element in the normalizer. Being an element in the normalizer means an element with which you can conjugate everything. You can multiply this element with everything you have. That's the advantage of having elements in this normalizer. So satisfying these conditions. So these elements in the normalizer define the lack of T from being a homomorphism, right? So T of GH and TG composed with TH are homotopic, but maybe not the same, right? So this is a normalization axiom. So T of one is the identity, etc. And then there is a cocycle condition that makes all these things work, right? So this is, you recognize this is a free cocycle, which is actually a boundary, right? So for the notation, we will simply write Gx like this for the action of the element G in this simplicial set M, right? Like this. So if G is in H and X is in any simplex, so just to short the notation.
Can I ask a question? Sorry.
Sure.
So here in the previous slide, the twisting function that you mentioned in the first place, that's the ordinary one that is used for.
Yeah, the twisting function
hydration.
that is defined. So in the original paper by Barat, Guggenheim, and Moore,
okay.
or
okay,
in you can see it in May's book on simplicial objects, right? So
okay.
it's the classical, yeah.
So is the idea of this definition is it that in the case of partial groups, that's only the only thing that we need to keep track of is the low dimensional
exactly.
Okay.
And this is all due to this say spine operator, which is injective, right? And somehow what happens in higher simplices somehow is controlled from lower simplices, right?
Okay.
So yeah,
okay.
So the twisting function is defined in all dimensions at once, right? And we only need this simplified definition on H1 and H2. There is a slight difference between these axioms and the corresponding axioms for twisting functions, even in dimensions 1 and 2, but very minor. So here is the theorem. So given partial groups, assume we have a twisting pair, then this defines an extension, which is written like that. And we can define this extension algebraically, right? So the simplices are of this form, right? And satisfying these conditions. So of course, G1, Gn will form a simplex in Hn, but the condition on the X size is more complicated. We claim the point is that this complicated simplex should be a simplex in a well-defined simplex in M, right? So you see, this means this is not just the product of simplices. So this is different from taking simplices in M and multiply by simplices in H, right? So you have to take care of which of these simplices are allowed, and this is given by condition 2, right? Once you have described this as a set, then you should tell with what is the phases and degeneracies. And essentially, I'm going to give you the product, which is essentially the differential of say of this simplex. H. So if you write the differential of 1, this is what we call the product, right? And then that's the formula that gives you this structure, right? So this is the formula that you compute out of the structure that you have. And then you can also work out a formula for the inverse element, right? Mm-hmm. And this is all in terms of the products of the inverse products and inverses in M and H separately, right? So the projection, there's no problem. It's just the final in the usual way, right? And there is no restriction. Okay, so so now given an extension, just any extension, we recall this means a fiber bundle, then there is an H twisting pair like this, and an equivalence of the extension of the total space in this fiber bundle and the partial group that we just defined, right? So every extension is of this form, right? And this means in particular that the total space of an extension of partial groups is again a partial group, right? So that's a nice result, I think. Okay, and then it comes the classification. Once you have worked out all these constructions, the idea here is to be able to compare the topological version of the classification and the algebraic version of the classification that you can find and in books in algebra. McLean's book, for instance, works out all this. And once you have that, the proof of this theorem works as in the classical case, right? So if you call this the set of equivalence classes of extensions, then if this is non-empty, if and only if a certain obstruction in H3 vanishes, right? Like in the classical case. And when this is non-empty, so essentially there is a bijection between this set and H2 of the base space with coefficients in the center of the fiber, right? So that's the classical theorem for extensions of finite groups, right? Okay, so do I have some time? Well, a few minutes. So I can say a few words on regular split extensions of partial groups and sections. So, given a partial group and a partial subgroup, we'll define something which somehow generalizes what we said the normalizer before. And this is the normalizer of M in E, right? So the normalizer of the small thing in the big one, right? So this is the simplices in E, such that each one of the edges defines a homotopy of the inclusion of M in E, right? Homotopy of the inclusion. So in fact, what this is doing is defining conjugation by such an element that is defined on the partial subgroup, but perhaps not in the whole partial group E, right? So when we have an extension of partial groups, it happens that this is a subgroup in E or subpartial group in E, and we do have an extension like this again. So this is inside M, and sorry, oh, there is some typo here because this is, oh no, yeah, it's okay, yeah, it's okay. So this is inside E, and this is inside M, right? So this is a sequence inside the other one, an extension inside the other one, right? And the point is that each element in here determines an automorphism like this in M, right? Which is conjugation by C, right? So you know that this is preparing for sections. So here's the definition. When we have an extension of partial groups and we have such a normalizer in E, normalizer of the small m, then a section is defined as usual. I mean, a map like this, right? Sigma, right? So we call this section regular if it factors through this normalizer, right? So we are saying, well, we have M, E, H, tau, and then there is a section, sigma, but here we have this normalizer, right? And then we say that this is regular if it factors like this, right? And this means, from what we have seen here, is that if we take an element in H, Y, and then we have sigma Y here, then this sigma Y acts by conjugation on M, right? Belongs to out M. So we have an action in this way. Somehow we get the action of the base on the fiber, right? And the extension is regular. The extension is regular split if it admits a regular section. So that's the standard split extension, regular split extension, as this is semi-direct product, right? And with all this theory behind, we can define it in the usual way, the semi-direct product, as these elements, such that this belongs to H, and then we have this technical condition to define the elements that are admissible in the semi-direct product, right? So and the action is given as we mentioned before. And we are sure that this is well defined as a partial group because this is this corresponds to the fiber bundle defined by the tautological twisting pair, right? Which is given by the action, which is an actual action because the section was regular. And then the homotopy we were taking before, eta, could be just the identity. That's nothing, it's a constant homotopy, right? And that's the classical way also. Right? So now, so the theorem is like this. So so given an extension of partial groups, so tau admits a regular section if and only if some given abstraction class vanishes, right? And notice that this is a normalizer of M. This might not be abelian, so this is non-abelian cohomology, right? Cohomology. So a regular section determines a homomorphism of partial groups, and then an isomorphism of regular split extensions. So so this means in any extension of partial groups, having a regular section, so the total space is the semi-direct product. It's isomorphic to the semi-direct product. Furthermore, there is a bijective correspondence between sections and yeah, oh, I forgot. Yeah, between the H1 of H with coefficients in M, and this is also defined in the usual way, but this is pretty technical. And I'm not going to write down equations now, because M is not only non-abelian, but it's also a partial group, right? But you can define derivations in this way, equivalence classes of derivations, and this gives you a definition of H1. And this turns out to be the set of equivalence classes of sections, right? Under this bijection, regular derivations corresponds to regular sections. And regular derivations are those having image in the normalizer, and this work like the classical derivations in group theory, right? And I think I'm, 2 minutes to say thank you. Okay, that's all. So thank you for your patience.
All right.
There are questions.
Thank you, Carlos. Are there any questions?
Yeah, I have a question. Hello?
Hello?
Yes. So if we restrict our attention to some sort of abelian,
Oops. No, I can.
Yes.
I can hear.
Okay. Could you hear me now?
No.
No.
Let me change to my laptop from the iPad, and maybe it's going to be better.
Okay, sure. Thanks. So
sorry, I have to mute here before. Okay. I'm sorry. Let me see if this works now. Okay, let's do something. maybe just close
Okay, so-
the connection in my iPad,
Mhm.
right? And then open the slides on the desktop, right? So.
So my question is, if we consider only the abelian partial groups, then does it just reduce to simplicial abelian groups or not?
Okay, so I have only one. I hope it works now.
Mm-hmm.
That's it.
Yeah.
Sorry about that.
That's all right.
So yeah, so please go ahead.
Yes. So my question is, if we consider only abelian partial groups, then what happens? Does it do they simply reduce to like simplicial abelian groups or not?
I didn't check, but my guess is that everything will reduce to the, like in the classical case.
Okay, so there won't be anything new in that case, right? So the only interesting cases are.
Well, there might be extensions, say, of I mean everything restricted to abelian groups. So you want extensions such that total space is again abelian, right? So the extension is right. So yeah. So what happens?
Okay, I have a related question. Maybe it might help.
Yeah.
So the example that you mentioned, which is, we call that the commutative classifying space, right? The BCOMG. So the n tuples are commuting pairs. So is it a commutative partial monoid? If it is so, then it is not a classifying space of an abelian group in general, right? So
it is this one. Well, yeah, it is abelian. Let me just try to share again the.
So what does abelian mean here? It means that if a simplex exists, then you can permute the spine any way you
Well, I could say
permutations
that,
also exist.
that,
Don't have the same product.
Yeah, that abelian would mean that once you have two elements that you can multiply, you can also multiply them the other way around, and the product is the same.
Oh, I thought you would require that for all lengths of products, not just length 2. Not just for pairs of elements.
Well, yeah, if you want to define all higher simplices, then you have sequences of any length, right? So n simplices will be something like G1 bar, G2 bar, Gn, and all of them commute among them, right? But imagine you start taking phases of this, right? Applying differentials. So you start multiplying elements 2 by 2. The new elements you are getting continue being commutative, so they are inside this simplicial set. So phases are well defined until you arrive to say 2 simplices, and this is the basic multiplication that you have. Because so if you have a simplex G1 GH, for instance, then the product is so imagine a triangle with one edge is G, the other is H, and the back one is GH. Right, so the product of G and H is this back simplex GH. So then, but this tells you how it works in higher dimensions, because if you have this GH in the middle of a larger simplex, so the differential DI affecting these 2 simplices is going to be the same, G times H, right?
Right.
There's no other way. So this controls what the products are. What the higher simplices tell you is when the product are allowed and when the product does not exist somehow, right? But the control of the product is in dimension 2 and 1, dimension 2 and 1, right? So to make it abelian, I would say I didn't think about before, right? But my guess is that this will mean that once you have x times y, you also can define y times x, and the result is the same. So you have a simplex which is from 0 to the first edge is x, second is y, and then there is a back edge. But there is another simplex which is y and then x, which is not exactly the same, right? And they have to have the back edge in common.
Yeah.
Right. Unfortunately, I had to disconnect my iPad. Otherwise, I could draw a picture. That's pretty clear. But imagine a square with a diagonal. In the diagonal, you will write xy equals yx, and then in the sides you will have x and y. But this will be like two simplices. I think it will be two different simplices. And this would be a billion. Then I think that the classification of extensions will be what I have described in general, but adapt to the case to the billion case. For instance, the action that I've been describing will be trivial action. So everything will be easier, but yeah. So the extensions will be, there is no obstruction to the existence of the extension in the case of the abelian case. So you always have extensions. And then extensions will be classified by H2 of the quotient group with coefficients in the kernel group, which is the fiber, say, which is abelian, so the center is itself somehow. Well, maybe not, because in the center you want elements that with which you can multiply everything. So you have to be careful with this, right? So the center, even in the abelian case, the center might be smaller. For instance, in the case of this space of commuting elements, I think the center is going to be the center of the group G.
Yeah.
And not the whole thing. Although when you have elements there and you multiply, if you can multiply them, then they commute. But the real center, I think, is just the center of the group.
Yeah, I think that's right. It's elements that you could add to any commuting set to still get a commuting set.
I didn't write down anything about this because, but I think it's like that.
Okay, thank you.
Yeah, thank you.
We have maybe one more question from Antonio. You raise your hand.
Yeah. Yes, right. Okay, so Carlos, I was thinking whether in this fibration you described, the group NM is just the fundamental group of the partial group as a topological space, as a simplicial space.
The group which?
NM. The normalizer of M.
Yeah, the normalizer
would be the fundamental group of M as a topological space.
It could well be. I didn't think about. That's
it's looked like, right?
That's a good guess, indeed. Yeah.
Because that's what's going on at the level of group sector.
I don't know. Yeah, right. It could be. There's always a problem with these partial groups. This is that are not Kan complexes.
Yeah, but then I guess that's what
group.
I mean. Probably the fundamental group as a simplicial complex, or simplicial fundamental groups.
Right. Exactly. Yeah, it makes sense, but I don't really know. Yeah.
Okay. Thanks.
Thank you.
I have to check how to bajar la mano.
Are there any more questions?
I wanted to ask one thing. Can you have two honest groups and an extension which is partial?
Well, I don't think so. If you look at the classification of extensions,
right, the classifications seem to.
The one for partial groups reduces in the case of honest groups to the classification of extensions of groups. So the extension of two groups will be a group again.
Okay.
Even
Can I also ask something? So the notion of a partial monoid that you're using, it's more general than the conventional one that's been used in the literature, right? Because there's this extra condition about the associativity, which doesn't hold for these examples. That, for example, for BCom, it doesn't hold, right?
The associativity.
Yeah.
Well, the associativity in a partial monoid means, well, you have to be careful when you define the associativity in the as in the classical way of group theory. The formula holds when all products are allowed. Otherwise, it doesn't. Right. So it might be that you can multiply A and B and then by C, but you cannot do the multiplication of A and then B and C.
Yeah.
But once you have this simplicial set, this associativity is taken care by the simplicial identities between phases and degeneracies.
But it is weaker though, right? It is weaker. It is weaker than this requirement.
Is it weaker? I thought it was equivalent.
Yeah, so that's what I was trying to say. So let's consider the example of BCom. Think of the n tuples of commuting elements. And in this case, what is the associativity rule dictated by the simplicial set? And what is the associativity rule dictated by a conventional monoid?
Yeah.
The one dictated by the conventional monoid, it doesn't hold, right? Because you can have three elements which are pairwise commutes. So you can have three elements where the first two commutes and the last one commutes with the product.
Right.
But it doesn't hold the other way around. So it is not associative in the conventional sense, but it holds, it fits into your definition of a partial monoid. Because it is
I'm not so sure, because in order to write this, you need to have, say, if you have these three elements, what you need in this simplicial set is to have a three simplex, where the spine operator is the sequence of these three elements.
Yeah.
And then if you start completing these three simplex, writing the multiplications, right, in the back edge, at the end you will have the associativity rule. But if you don't have these three simplex, then I don't know what can happen. If you don't have the three simplex, I mean, if you write these three edges, right, and you start completing this to a three simplex. If you cannot fill in with the three simplex, then there is no, I don't see how you can find that this associativity rule holds.
So wait, am I understanding you correctly, Chihan, that you're saying that in the traditional definition of partial monoid, it's required that if you can form the product A times B, and you can also form the product AB times C?
Yeah,
in that case, you can also form BC and then A times B.
Well, I don't really know if there is
that does seem stronger than
a different version of partial monoid than the one by Andy Chermak. So as far as I remember, what Andy Chermak claims is that you should be able to multiply ABC.
Right.
So
that's the simplicial set version,
which is equivalent to say you have the three simplex.
Yeah.
Right.
Okay.
So he describes the multiplication as taking just the collection of words on the elements in the monoid, right? And then he defines what he calls a domain of multiplication, which is a subset of the collection of words, right? And he says, well, if ABC is a word, then the associativity rule should say this, this, and that. Something like that. I'm telling this by memory, right? Something like that. And I think this is just the same as saying, well, if you have the 3 simplex, then you check that in this back H, you find that AB times C is the same as A times BC.
Okay. Okay, thank you.
I don't
All
know.
right.
There might be a different definition of partial monoid. Yeah, I don't know.
Okay, so let's just wrap it up. Thank you again, Carlos, for your talk.
Thank you.
So I don't know, should we meet in 30 minutes or in 28 minutes? I don't never know what to do. But
I think
okay,
30 makes more sense because the research seminars schedule is the one we should take
at that time. Okay, sure.
Yeah.
All right. So we'll meet in, I guess, 28 minutes. Okay. See you then, guys.
See you then.